So we have seen the most important functions available in AAL through the convergence sublayer and the segmentation and reassembly. Just few details to finish this part. So here you see some packet format. Now, remember, we are observing what we can carry in 48 bytes. Now, if you remember something about the protocol layer concept, what's happening when you have several layers, one on top of the other one, is that so you have a given set of layers here, and any layer is taking the data coming. We are looking at the data flow from top to the bottom. So user generates data. Any layer is taking the data coming from the above layer, is adding some information, which is all of the header we have seen up to now. So any layer has a different set of header fields depending on the functions that you have to run. So we have seen in FrameGlade there was a CRC for error detection. We have seen labels for addressing and many other things. And this data goes to the below layer as the data part for, so this is layer I, this is layer I minus 1, I minus 2, and this layer is adding some additional information and so on and so forth, right? So any layer is adding something. So when you go on the wire, you have a huge data which is made by user data plus layers added by any headers added by any layer in your architecture. Okay, so that's the layering principle in protocols. So it means here that since AAL is on top of ATM, okay, whatever you generate at the AAL level is carried by ATM in 48 bytes. Okay? So we need somehow to deal with segmentation and reassembly, and we have to deal with this functionality we have described: synchronization recovery, timestamping, sequence numbering, etc., etc. So here you will find within those 48 bytes, which are the bytes we are using to do what for the different AAL. So let's take an example here. In AAL2, we see that only 44 bytes are really used for carrying user data. So the segmentation process is actually taking the packet and creating chunks of 44 bytes. Why? Because the remaining 4 are used for sequence number, okay, for CRC, error detection, okay, which we don't have in AAL1, so we don't have this field. And in particular, this length indicator field here, you see that this is shared also with AAL3 and 4, is there because whenever you take, well, you have the reminder, okay? Whenever you take a packet of a given size and you chop it in 44 or 48 or whatever number is the fixed size, you may have a reminder, correct? Which may be 0 if the original packet was an integer multiple of that size, otherwise it's something which is ranging from 0 up to the packet size. But still, the packet that you generate to carry the last part of this packet, so the last cell, should be of 48 bytes. It means that those 44 bytes should be there, but not all of them are part of the original packet. To put it simple, something is simple to see as a graph. If you have this original packet and you have to chop in integer multiple of something, okay, I don't believe it. Well, suppose that this is a reminder, okay, there is a reminder here, and suppose that the original size is 48, so this is 48, this is 48, this is 48, and this is only 42. Still, you fill up 42 bytes with data, and 6 bytes you have to write something, which is of course dummy bytes. It's not contained any useful data, but they are still there because the packet size should be 48. So how do you know how many of those 48 are real data and are dummy bytes? How do you know as a receiver? You have no idea, right? So you need to write this information. So every cell is carrying a length indicator field which tells of those 44 bytes how many are really user data and how many are dummy bits, something that you have added because you need to make the packet size of an integer multiple of something. Okay? So any of those packets carry information which is actually always 44, 44, 44, 44, 44, except for the last cell derived from that original packet, in which you may have 42, 41, 30, I don't know, it depends. Any number from 1 to 43. Okay? That's the length indicator. CRC is to detect errors, and you see that this structure is shared also with the AAL3 and 4, which is also numbering packets. This is for data traffic, so there is no synchronization, no timestamp, nothing like that. But you still want to put packets in the proper ordering. Okay, so you have a sequence numbering features also in AAL3 and 4. So if we focus now only on the data traffic, so AAL3 and 4, it is working, so there are no synchronization, no timestamp recovery, no function like that. What you are really doing is that you are numbering this packet as packet 0, packet 1, packet 2, and packet 3. This is the sequence number you put in AAL3 and 4. Okay? Then you have the CRC to detect for check for errors. And you have the length indicator, which is always 44, if not for the last packet. Because the last packet size, it depends. So we have a number, we don't know which number is there. This is how AAL3-4 is working. You may say, why do we need the sequence number since we have a virtual circuit? AAL is based on virtual circuit, so there is an in-sequence guarantee. Packets are not arriving out of order. It's not possible. But you still may have some packet missing. Okay? So if you have packet missing, you will detect them through the sequence number. And if there is a single cell missing while you are trying to rebuild the packet, at the end you will drop everything. Okay? So in the transmission phase, you take the packet, you chop it in 44 integer multiples, you put sequence numbers 0, 1, 2, 3, up to the number this is coming out. On every cell, you have a CRC to detect for errors and eventually to drop the packets for errors. And on the receiving side, you will rebuild the packets, you will check the sequence number, you will check the CRC, you will detect the packet length, the length indicator on the last cell, you will rebuild everything, and if everything was fine, you have the original packet, which is this one here. Okay? Otherwise, if anything is missing, if there is any error on any of those cells, you will drop everything. You will not give this packet to the upper layer. Is it clear? Segmentation and reassembly process. Fine? Any question? Now, if this is true, the question would be, how can AAL5 work with no header? There is no overhead, you see? All of those 48 bytes are user data. How this is possible? How can we implement the function of AAL5, which is segmentation and reassembly, without any overhead? Well, here is the trick. So this is what AAL3 and 4 is doing, right? You have this header in which you have the packet number, you have this trailer in which you have the length indicator, the CRC, and some other fields. What is doing AAL5? Okay, AAL5 is taking the upper layer data. This is the CS layer payload. So everything is coming from the above, is the so-called CS layer payload. CS stands for convergence sublayer. It's one of the two sublayers of AAL. You add to this one a single length indicator. Okay? You add to this packet a single CRC for error detection. So the error detection is not on any single cell, it's on the full packet that you rebuild at the receiving end. Okay? So you add one CRC and one length indicator. So we can get rid of the CRC on any cell. So that's why there is no CRC on any cell. So we can get rid of this. We have to deal now how we solve the problem of sequence numbering. And also we have to deal with the problem of the length indicator, the last cell, the reminder. How can we ensure that there is no reminder? We have a padding field here, which is ranging from 0 up to 47 bytes. Whenever you find a padding field in any technology, is there to ensure that the total size of the packet is an integer multiple of something. Any padding field in any technology is there for this reason. So this padding field, which is ranging from 0 to 47, ensures that the total packet length is an integer multiple of 48. So any data in those cells is useful to rebuild this packet here. So there is no need to put a length indicator in any of them, because always 48 bytes are useful. You will detect eventual padding here at the CS sublayer. Is it clear? So we can get rid of the CRC and of the length indicator in these cells. So we don't need them anymore. We still have some overhead, of course, it's here. But it's not repeated on any cell. Now the advantage is that a single CRC in terms of protection against error is better than independent CRC on any cell. So we have even better error protection features, okay, with less overhead. Here, less overhead. Of course, we have some additional overhead here. Clear? Up to now, is this clear? Now the last point is, how about the sequence number? How can we detect errors, missing packets? The packets are arriving in order, so we really don't need a sequence number. If not to detect this packet is missing, and when a packet is missing, it may be missing for transmission errors or for queuing overflow. We don't know. We don't get it. That's the only information we have. That packet is missing. So what happens in this AAL5 if there is a packet missing? A cell missing, sorry. You will get those cells, except one. You don't know which one. You put them together trying to rebuild this original packet. Of course, the length will be wrong because you have missing bytes. The CRC will be wrong. And so you will detect that this packet must be dropped, which is exactly the same thing you will do with AAL3 and 4. So if there is a sequence error in the sense that there is some data missing, you will detect it here anyway, and you will drop everything, without the need of really knowing that the cell lost was cell 22. Who cares? At the end, I'm dropping everything anyway. Is it clear? There is only one issue, one problem. Suppose that you generate a set of packets, one after the other one on the same virtual circuit, and you send them in this fashion here. Okay? How do you detect packet boundaries? So suppose that the packet size is 100. You want to generate 3 packets, send 3 packets on the virtual circuit. You will generate 300 cells that you must group 100 plus 100 plus 100 independently to rebuild the original 3 packets, correct? How do we detect packet boundaries in the cell stream? How do we know that the packet size for the first one is 100 cells, for the second one is 80 cells, for the third one is 300 cells because maybe the original packet size was variable? How do we know that? We are receiving 300 cells, that's it, there is no other information. How we are able to detect packet boundaries in the cell stream? Is it clear the problem? Is it clear or not? We are getting a given number of cells on the virtual circuit, one after the other one. Those cells were generated originally by 3 CS packets. Suppose that every CS packet requires 100 cells. We are generating 300 ATM cells, sending them on the same virtual circuit, and the receiver is getting 300 cells. How do you know that you have to try to put 100 cells together to rebuild the first packet, then the next 100 cells together to rebuild? You have no idea. In the previous case, you have sequence numbers. 1, 2, 3, 4, 5 up to 10, and then again 1, 2, 3, 4, 5 up to 10. Every packet generates a different independent sequence number scheme, correct? So you have a perfect idea about what to do. Okay? You even had, I didn't mention that, but you even had some additional information in the header through this field, which tells you this is the first cell in these packets. This is the middle cell, this is the last cell. So you know exactly how to detect from the cell stream the original packet. There is no doubt. But here we have no idea. How do we do that? Now that's the trick. We have one bit here. If you remember, we have seen the ATM field payload type. And I told you there is one additional bit for the user data cells. I will explain you later how we are going to use it. Okay? So AAL5 is using that bit in the ATM header to say this is the last cell of a packet. So what do you do is that you keep getting cells one after the other one until you get a cell with this bit set to 1. That's the last one. So you put together everything up to this cell in the same attempt to rebuild this packet. If succeeds, good. If there is anything wrong, you drop everything. And then you start again. So this bit here tells you that's the last cell of the packet. And of course, the next one is the first cell in the next packet, and so on and so forth. Clear? So yes? Because ATM is based on virtuous circuit technology, and in virtuous circuit, by definition, all of the packets follow the same path. Since normally, unless you do something very, very strange, switches don't exchange packet positions, normally don't do that. If you have this guarantee, the packet generation process happens in order, the packet reception process happens in the same order. You may have misses. You may have holes in your sequence. This may happen, but not exchange of packet ordering. So if you have a virtual circuit, or if you have a physical link, you know that if you are receiving packet 0, 1, 2, 4, packet 3 is not going to be received later. That's a guarantee that you have in circuit switching, in virtual circuits.
Because even though a node is crossed by more than one virtual circuit, there is, however, the allocation of a guaranteed bit rate.
No. All of the packets for a given virtual circuit follow the same flow. So what may happen is that one packet reaches this node and you will find 10 packets in the queue, so you will have a given delay. The next packet maybe will find 100 packets in the queue and will find a different delay. Okay, and that's the effect of the other virtual circuit. But two packets received one after the other one on that node, we will put these in this buffer one after the other one, so there will be no overtaking. You may have different delays, but no overtaking. Okay? So if you miss one sequence number, that packet has been lost, either dropped in a queue or you have a transmission error. For sure, because the order is guaranteed. Okay? Not in general. If you have a packet switched network with datagram service, this is not true. So you cannot ensure that. You cannot infer that. Yes? Yeah, that's exactly the point. If you miss the last packet, there is one problem. In the previous case, if you miss the last packet, you will drop this packet here, of course, but you will detect the initial cell of the next packet. So the next packet will be received properly. In this case, not. Why? Because you will put together all of the cells of these packets, except the last one, plus all of the cells of the next packet, thinking that they belong to the same one. And of course, putting everything together will create a CS layer payload, which is going to be much longer than this length with a wrong CRC, and you will drop two packets. So we will lose this. Okay? So that's true. That's what we lose. If you lose the last cell of a packet, you will lose two packets, not only the first one, because the second one will also be dropped. You are not able to detect that. That's the only thing that you lose. Okay? Still is so more efficient. Think that if you were using AAL3 and 4, you are going to waste another 10%, because you are wasting 10% for ATM, actually a little bit more than that, 5 over 53. So 5 of overhead for 48 of data. Okay? Furthermore, of this 48, 4 bytes over 48 will be, with AAL3, lost again for overhead. So it's roughly another 10%. So you see that it's starting to become a little bit significant. Then you will have the overhead of the physical layer. If it is SDH, you can go back to the format of the SDH. We see that there are several slots devoted to control, overhead, etc., etc. This is again something that you subtract from the user. So by keep subtracting, you see that at the end, you have 1 gigabit link, and then you lose 20, 25, 30%. So it started to become a little bit too much. So that's why AAL5 is much more preferred, because at least you don't waste this 10% for something that at the end is happen very rarely. Because packet drops in terms of error, bit errors are very, very rare. And dropping packets in a queue, if you have a well-controlled network, which we hope to, if you want to provide quality, we must control our network. Controlling means avoiding packet drops. If you start having packet drops, it's because you have a congestion. Congestion happens if the network is not controlled. So at the end, all of this probability of having packet losses, cell losses is very low. And so who cares? It's not a big deal. It doesn't make sense to make all of those efforts to ensure that you are so able to detect errors when errors are such an unlikely event. Okay? So that was a summary of the AAL. So lesson learned from AAL. We have several AALs for different types of applications, family of applications, of course. Multimedia ones, which are providing synchronization recovery, is not written here. Sequence number and time stamping. Sequence number and time stamping are here. Synchronization is obtained using few bits on different cells. So the synchronization information exploits few bits on different cells to transfer this information. It's like what we do in TDM. If you remember TDM scheme in PDH, we say that we have 24 slots of 8 bits, and 1 bit is devoted to signaling, which means that if you want to send the signal information, you spread it in several frames. 1 bit here, and here is something similar. Okay, so synchronization recovery, sequence number, 8 time stamping, and for multimedia. Error detection for the data part, and for all of them, segmentation and reassembly. Okay? And that's it. So that's a summary of things that we have said, but it's important to remember. What is broadband ISDN today? Is really this end-to-end single architecture that allows you to have a tight control user to user? The answer is no, because it's not the only technology. Is it still used? The answer is yes, a lot, mainly as an alternative to frame relay to create logical topology on the so-called transport portion of the network. The technology used in the transport portion of the network are typically very different from the one we use in the access. In the access today, mostly we use at home ADSL, which is a given physical layer, and on top of that you may have Ethernet packet or ATM cells when you generate data. That depends. In some cases, very rarely use ISDN, but today is very, very unlikely. Or in small offices or in companies, you access the network through the Ethernet standard. It can be gigabit Ethernet, it can be traditional Ethernet, it depends. Okay? These are the two mainly widely used access technology. On the transport portion, you will find a lot of frame relay and ATM. In some cases, in some peculiar architecture, we still find ISDN in many cases on the transport part, within the core part of the network. Okay? We are mainly focusing here on the transport part of the network, where the control is difficult, because we are sharing of resources. On the access, typically you have resources which are dedicated to the single user, and so in that case the control is not so complex. That's why we mainly focus on the transport part. Okay? From the performance point of view, if you are only focusing on data transfer, I want to highlight very clearly that there is no benefit in using ATM with respect to frame relay, if not from the cost of the equipment point of view or any other issue that you may have, but from only the performance point of view. Due to the segmentation process that we must have in ATM, we are going to lose something in terms of performance. Okay? Then there are other issues that may be cost, that may be the fact that you want to have a single technology in your network because you don't want to deal with different technologies. ATM has a lot of potential that frame relay does not provide in terms of quality provisioning. So if you want to provide quality, clearly exploiting ATM is a better choice than frame relay. Okay? But if you are only using ATM as an alternative layer 2 to transfer packets for file transfer best effort, you have only problems. You don't gain anything. If you are lucky and clever, you get the same performance that you can get in frame relay due to the fact that the fixed packet size of small size creates a lot of problems like user traffic and more losses. Okay? So if you are using ATM, there should be some other reason to do that, not from the performance point of view for data transfer. Okay? So this is a summary of some of the aspects of how today broadband ISDN is exploited. It's actually very often we are not talking about broadband ISDN anymore. Very often you say that's an ATM network. Okay? Like very often you say you have an ADSL access. ADSL access actually is referring to the physical layer, right? Then on top of that we have Ethernet packets or ATM, but we are using ADSL, which properly is a name of a physical layer to identify the architecture. And with broadband ISDN something similar is happening. We are very often talking about ATM networks, which is not properly correct, but that's what we use today as a jargon. Okay? Any question, any doubt, any curiosity? No. Okay, we are almost done. We still have to review a couple of things. One is a little bit about local area networks, and there are many details in this slide. I don't want to go very deeply on all of them, but it's important to fix some concept about that. And then finally, a short review about the internet architecture in terms of IP and TCP, because as I said today, the de facto integrated network is the internet architecture. So we need to make sure that we know the basics of the internet and to understand why and how we have to evolve to make it a quality of service oriented network if you want to do that. So let's start with the local area networks. Well, I guess that most of you know and remember what a local area network means. Is first of all a small size network. So we are focusing on a small portion of a network, few kilometers. And originally, at least originally, the idea was to have a shared medium. So a good example of a local area network is this room. In this room we have a small area and we have a single shared medium. And you know which is the problem. The problem is that we have to organize ourselves in order to make sure that we are speaking one at a time. Otherwise there is a lot of confusion. Otherwise we are not able to receive any signal. So that's the problem of shared medium. The beauty of shared medium is that the cost for me, which I am a heavy speaker, to communicate with you is the same whether in this room you have 10, 20, 300 or 1 million. Doesn't make any difference. Well, 1 million might make some difference, but it doesn't scale the difficulty in sending the data with the number of receivers. Okay? One receiver, K receiver with K large is the same. Just one transmission, everybody is receiving it. And that's not true for all of the other technology we have seen. If I want to send one data to K destinations, in any of the technology we have discussed up to now, we need to create K independent virtual circuits and to duplicate this information to reach all of the users, which is a complexity which we don't have it here. So the broadcast medium, of course, is a limitation. We have only one channel for everybody. So that may be a strong performance limitation. But it has also some advantages, okay? And why originally only a shared medium was available? Well, first of all, mainly because the traffic was really bursty. So we have a shared medium. It's not a multiplexing problem. It's a multiple access because we have several transceivers which are located in different points of the network. And we know that we have techniques like the TDM or TDMA, which can be adopted, right? However, a statistical or deterministic solution will not work. And why? Because the traffic is bursting. What does it mean? Most of the time we are doing nothing, like you in this room, right? Most of the time you are not talking, unfortunately. Sometimes you want to say something. So most of the time there is no traffic, if it was not for me. But when you wake up and you want to send, it would be nice for you to have a significantly high speed. So we have a single shared medium of relatively high speed shared among silent users, which are very bursty. Most of the time you do nothing. When you wake up, very likely you will be the only one to wake up because everybody is typically silent. And at that point, you can get the full bit rate of the link. Then another user wakes up, and again, it will very likely be the only one that wakes up and will get a huge bandwidth to send the data. If two users wake up at the same time, then we have to solve the problem to ensure that they do not overlap in time. But this is a very unlikely event. Three users waking up at the same time, even more unlikely. Okay? So it works well, a single shared medium in that scenario. Good. Furthermore, it's very useful for broadcast multi-code transmission. The only drawback is that if in this room I want to say something to one of you, I have to address my voice and to make it clear that I'm talking only to you. So when he made this bad joke this morning, and I want to tell something to him and to say, hey, that was a very bad joke, and that was only for him. I have to address this communication, okay? It's only bad because I was not able to understand it, of course. So that's the only thing. The so-called unicast transmission, which is a transmission from a single source to a specific destination, must carry the destination address. Because since that medium physically gives this information to everybody, I need to do that. Otherwise, everybody may think that this information is for that receiver as well. Okay? And this, of course, creates also some potential issues in terms of security. Because everybody is reaching the traffic destined to everybody else in that single shared medium. Okay? So that may be an issue from the security perspective or the protection of the information perspective. Okay? And, oh, nice. See next slide, and there is no next slide. No, there is a slide, okay, but I thought that the slide had a picture, but it does not have it. So, we have not dealt at all up to now with multicast or broadcast transmission, but always we have made example about a point-to-point communication, right? All the time, that's called unicast. One source, one destination, possibly bidirectional, but one transmitter, one receiver. Okay? That's the case in most of the communication, but that's not the only possibility. There are other scenarios in which you want to reach a group of users. Or in some other scenarios, you want to send a message to all of the users in a given area of the network, okay, in a given portion. That's called broadcast message, okay? An alarm. When there is an alarm, you want to say that to everybody, right? For example. Multicast, example of multicast grouping, well, a video conference. If you want to set up a video conference among K of us in this room, we need to have what's so-called a multicast transmission, something which is not for everybody, is not for only one of you, it's for a group of receivers. That's called multicast, okay? Now, multicast raises some issues in meshed topology. Why? Example. So we are talking about multicast. If I can get the pen, yes, I got it. Okay. So let me give you an example, which is the example that I'm always using all the time. I'm getting old and I'm getting every day more boring. So I'm repeating myself all of the time. So I have several users here, right? And suppose that this is the source of my video conference. It's actually not a video conference, it's a video streaming. I'm talking and I'm sending my information to a subset of users, okay? And suppose that the subset of users I want to receive are those users which I'm highlighting here in red, okay? This user, this user, these users, and these users, okay? So in this case, my set of destination k is equal to 4, okay? Good. You may say, well, what's the big deal? I want to generate this information and I want to reach k receiver. I can open k independent connections, right? K independent virtual circuit, for example, and send to each of those users the data. So I'm treating a multicast as k unicast independent connections, right? Why not? I can do that, correct? So I can create 4 independent virtual circuits in our case, and at the source generate on each virtual circuit and duplicate the same information if I want to send to them the same information. Okay? That of course is possible. That can be done. Which are the drawbacks? Well, first of all, we are going to do something like that, right? So we are creating 4 virtual circuits which will require the same amount of bandwidth, the same bit rate, right? This bit rate, if this is a video conference, may not be negligible because that may imply video, okay? So I'm asking from the network to support k times the video bit rate if I have k users. Now suppose that the video bit rate is few megabits, let's say 5 megabits, because I'm compressing it. So I'm using compression techniques to reduce the bit rate, okay? So it's 5 megabits, and I have 4 users, okay? Instead of using 5 megabits through the network, I'm requiring to the network to create, to reserve an amount of resources up to 20. Now it's maybe a little bit less, but roughly speaking is linearly scaling with the number of receivers, okay? So 20 megabits is maybe okay, but what happens if k is 100? Or 1000. So this is not scaling with the multicast size, because the amount of resources you ask from the network scales linearly with the number of receivers. So if this is a heavy flow, which requires a significant non-negligible bit rate, and the size of the multicast group is significant, this is not going to work. Or, if you want, it's going to work, but only requiring a huge amount of resources from the network. That's not a good way of doing that. Okay? And a similar issue you have it here at the receiver, sorry, at the transmitter, because the transmitter must make k copies of each packet, right? More or less at the same time. And again, if k is small, it may not be a problem. If k becomes hundreds of thousands, then may become another problem. Because suppose that this bit rate is significant, so it's 10 megabits per second, and k is 100. That becomes gigabit. And I may not have such a speed in the access, or I may not be able at my transmitter side, in terms of computational resources, to be able to generate such a large bit rate. Okay? So that doesn't scale for 2 reasons. Does not scale in the network, and does not scale at the transmitter side, for large k and for bit rate of some significance. Okay? For example, for video traffic. But multicast is very much useful for video, right? Most of the time, we are using it for multimedia applications, which imply voice, very often also video and data. So what we can do as an alternative? Is there any alternative? The answer is yes. What you may do is something like that. You may create a single flow within your network and then split it when really needed, creating what is called a multicast tree. Okay? So you generate a single flow at the source, then you move in your network, and then when it is needed, for example, in this node here, you duplicate. Okay? You duplicate the packets. Is it clear? Yes. You must set up exactly the same process that you do when you set up a virtual circuit, in which you configure the node. In order to do that, you need to configure this tree. So you need to go to the node, and this node should have the ability of making copies. So this is a new requirement we put on nodes. Nodes must support multicast. It means you get one packet, and instead of forwarding it only, you may need to make several copies. So it needs support from the network. Okay? And of course, you need to configure that. Otherwise, as you said, how does the node know that? So the first hypothesis is that you support multicast transmission in your node. This multicast tree must be set up, but also the previous communication must be set up. Okay? So you set up a tree instead of a path. What do you gain? Well, you gain the fact that you reduce the amount of network resources you require. Now, how much? It depends on how much you are able to build your tree. Now, if the destination users are very much spread out everywhere, you don't gain a lot, of course. If they are very much concentrated in a given area, you may gain a factor of k almost. It depends. In general, you gain. Of course, at the end, you need to generate k flows, but you are generating them as close to the receiver as possible. And you distribute this task that originally was here only at the transmitter to several nodes. So you distribute this duplication task in your network. Okay? So that case is good from the user because you don't need to generate several flows. Still, you pay the price of generating only one. It's good from the network manager because you are supporting that flow with a reduced amount of resources. It makes the network management more complex because you have to deal with multicast in your network. So you need to detect multicast address, you need to set up your nodes to create copies, which is more complex than simply switching one packet, of course. So these are the drawbacks. Okay? In general, dealing with multicast in network is more complex. Okay? As far as I know, today, the direct support for multicast, which means multicast tree creation and duplication, is not really used in practice today. So there is no direct multicast support within the network at the node level and at the setup of the multicast tree. So what you typically do, you act at the application level. You have several, suppose that this is a video streaming, okay? You have several video servers distributed, which are not managed by the network provider. They are managed by the service provider, which distribute this information among servers, and then servers locally serve the users. So you see that at the end, you create a tree among servers and from servers to the customers. It's a suboptimal solution because you don't have, if you wish, a server in every node. If you have a support in the network, you may have a server, a multicast server in every node. Because everywhere in any node you can make a duplication. Here you duplicate only in these servers, which of course are in a limited number, more limited number. So that's what practically today what we do in order to really support applications in which you have a large set of receivers. You deal it not within the network in the multicast addressing scheme, but a higher level by distributing through servers and then dealing with unicast connection within the network, but closer to the destination. That's the practical solution. And this has to deal with the fact that dealing with multicast or broadcast in meshed network is very difficult. It's much more complex. Whereas if you have a shared medium, you send one packet, the receiver is 1K or everybody, the cost is the same. One transmission, you reach everybody. Okay? That's one of the advantages of shared medium. Of course, they don't scale. You cannot have a single shared medium for the full internet, so it's not going to work on a very large set of users. We know that. But for a small portion of users, it may have some advantages. Okay? Is it clear? Any doubt, any question? So this is basically summarized in this slide, right? So multicast in mesh topology is more complex than in broadcast channels. You may treat the multicast traffic with a group size of k as k independent unicast connections. Okay? You have a scalability issue at the source, and you have a scalability issues in terms of how many resources we need in the network. Basically, you have k independent flows from the same source to different destinations. Better solution to create a multicast tree. The optimal tree definition is NP. NP means a problem that we are not able to solve in practice in reasonable time if the size of the problem of the network is large. If you want to make it broadcast instead, it is polynomial. We have a polynomial algorithm that is able to reach every node in an optimal fashion, okay? And that's called panning tree. Whereas if you want to have an optimal multicast tree, by optimal I mean, for example, the tree that minimizes the network resources, that problem is very complex, okay? And it requires network support in sense of setting up the tree and duplicating the packets, as we've said. So this is a summary of what we have discussed previously, okay? The last thing that I haven't said is that further complication is that typically these multicast groups are not static, but they are dynamic. So user leave, and that's fairly easy because you can cut some part of your tree. That's fairly easy. But user especially may join. And when a user joins, you have the problem of what to do. Because on the one hand, the optimal tree now may be completely different. So, but that implies destroying the previous tree and building a new one for everybody. Or you may have a suboptimal choice that is try to connect this user to the currently available tree, which in general is not the optimal solution. So you have to deal with this dynamism, okay? Which again makes the problem a little bit more complex. So these multicast trees must be managed over the time of the connection. Whereas in a point-to-point connection, either the connection is active or when it becomes inactive, you drop it and that's it. So you see that there are many reasons why dealing with multicast is much more complex than dealing with unicast. Okay? Any question? No. What time is it? Okay. Okay, so we have a single shared medium and we have the problem of multiple access. So we need to coordinate our transmitter in order to ensure that not more than one transmitter at a time is sending on that channel. If even two of them are sending at the same time, that's just waste of time because they need to retransmit and none of this information will be received. Even if you have only a partial superposition of the two signals, okay? The full packet is not received, so you have to drop everything. So we need to avoid that. We can do that through TDMA, FDMA, code division, multiplexing, whatever, multiple access, sorry, but that's not suited with respect to bursty traffic. The hypothesis is that here users wake up and go, wake up and sleep. So a static solution, a fixed predefined solution is not going to work, it's not efficient, we cannot accept it. It's simply not working. So you may say, well, so the static TDM you don't like. Why don't we take a dynamic TDM according to user needs, which is statistical TDM? The answer is yes, we would like to do that, but doing that in a centralized fashion is a nightmare. Why? Well, because we will need to collect information from all of the nodes about their needs, then assign transmission time, because of course you have a TDM frame. You can assign a different number of slots to different users, right? Matching their needs. So in this room we are 100, instead of having 100 slots, one slot for everybody, and if you use it good, otherwise it's wasted, you may say, no, we have only 3 users that want to send. You want to send 20, you want to send 10, and I want to send 50. Why not creating a frame in which I get 50, you get 20, you get 10? That's the good solution, right? And that makes sense. That can be done in a TDM fashion. We just need to redefine the frame according to user need. The problem is that you have to collect user need to make a decision, and in this case it's fairly easy, the decision, because we had a frame of 100 and we had less than 100 requests. But if we have more than 100 requests, you have to make choice, right? and we need an algorithm to do that, then we need to communicate this choice. And then finally you can send. And then again, we have to collect the new needs, etc., etc. So it's simply not going to work. So what we do is that we rely on distributed protocols, which are suboptimal, but much easier to be implemented, okay? And the goal is to emulate the statistical multiplexing. If we had a single transceiver, we will collect through several, we will collect in this single access point all of the packets from all of the users. If one user is generating a lot, we will send a lot of this packet. If you are not generating anything, you will not have any time available on the channel. That's perfectly what we want to do. Unfortunately, we have to deal with that in a distributed fashion, okay? Now, we do that through protocols. You may have heard about that. There are several protocols. The most popular one is the first one. Now, the first protocol we are going to revise in a moment is based on the random access idea. So the basic idea is that you don't try to coordinate a priori. You let the user more or less free. Now, at which degree of freedom we have to discuss, but the user may send, and the protocol comes into place only if there are problems. Problems means only if there is a superposition, I will do something. So it's a kind of optimistic approach, right? I trust you. I know that you are very silent most of the time, so I do nothing. So typically you wake up and you are the only one and you speak, and that's it. I don't need any coordination. Sometimes more than one of you want to speak and you will speak at the same time, then we will do something to solve the problem. But that's an unlikely scenario. That's the random access approach with several flavors. The other approach is strictly controlling to avoid it, and that's called ordered access, okay? So in several flavors, but the basic idea is that there is a permit to talk, okay? So this pen here is the power. Only who has the pen can speak. And since I have the pen, I keep speaking, okay? So, and if you want to be fair, we need to distribute this power, right? We need to distribute this potential transmission capability to everybody. So there is typically some control packet, which very often is called token, which is going to be going around in your network. And when you hold the token, you can talk. You can send the data. And then you have to release the token and so on and so forth. And these are ordered access. You avoid a priori any conflict because only one transmitter, the one which is holding the token, can speak. Of course, everything works only if there is only one token, if the token is not lost, because if you lose the token, nobody's talking anymore, and so on and so forth. So there are issues, but the concept is very simple, avoiding any a priori problem, okay? The third solution is nice because it looks a lot like ATM. It's based on a slotted approach. So you have a slotted transmission. So all of the packets are the same size. Let me just spend a few seconds to describe it. So let me take an example here. You have this type of topology, and the transmission happens in one direction. So there is a train of cells which propagates, and this cell is just a conventional signalization signal, right? So this is the start of the cell. You generate on the one end, and you propagate on this bus. And when you receive as a node, you know that this is the start of the cell. If you have something to send and the cell is empty, you can put your data there. If you receive something and the cell is not empty, because a node upstream of you has already sent the data, you have to leave it go, let it go. Okay? That's a slotted access. That's called empty slot protocol. So slot propagate in this direction. Of course, you will need another bus in the other direction to ensure that any node can talk with any other node. Otherwise, only node on the left-hand side can send on the right-hand side, and it's not going to work. But on the one of the two bus, you will check when you get a slot. If the slot is empty, you can put your data on it. If it's already filled up of data, you let it go. That's the basic idea. It's like a train which is moving, right? This is a railway, a train is moving, and you see carriages which may be empty or full. If they are empty, you can put your information on that. If it's already filled up, you let it go, and you let it go, and you let it go. Okay? That avoids any conflict, by definition. If it's empty, you can carry it on. If it's not empty, you let it go. Yes?
What's the mechanism to allow fairness?
Yeah, the issue, I don't want to spend too much time. The issue here is that it's unfair. Why it's unfair? Because if this guy, which is the first one, right, which received the carriages, is keep putting his data on any slot, everybody else is shut off. Because you will see something which is already carried in, filled in, and you cannot send your data. So in order to do that, the mechanism that you adopt is called reservation. So those nodes which are downstream in this direction sometimes reserve slots. They will say, hey, I need a slot. And they send this information on the other direction, right? And when you get this information, the upstream node will let one slot go, knowing that somebody else is going to use it. So it's not going to be wasted, because if you book it, it's because you have something to say. So if I let it go empty, then you will fill it up. So I'm not losing anything in terms of occupancy, in terms of efficiency, but I will allow everybody to send. Now, of course, it's not completely fair still, because since the time you make the reservation until you see the slot empty, it will take some time, whether this node does not have this problem. So there is still some delay, unfairness. But in terms of bit rate, that becomes fair. Okay? And there are no collisions, no conflicts. So that's an a priori scheme. You avoid conflicts on the reservation basis. When you need something, you ask and you will get it. With some delay, yeah, true. But remember, this is a small network, we have small delay, so it may be okay. Okay? As I say, the most popular one is the first one, not because it's the best in terms of performance, but because it's the best in terms of simplicity and ability to go to the market. So today we have random access protocol, which is called Ethernet, as you know, which is actually a CSMA CD in terms of access protocol, carrier sense multiple access with collision detection. It does not have the best throughput performance, no. Actually, it may even, if you don't control it, it may even lead to starvation, very bad performance. You need to control it to avoid it, otherwise it may lead to starvation, because it's based on this random access idea, right? The random access idea, which is you wake up and send, and if something bad happens, we will recover, works if really you are sending rarely. But if many of you want to send a lot of data, it's not going to work, because you keep waking up, sending, and creating a collision, which is zero throughput. Because if you have a collision, there is no data which are received. And if you don't avoid this, you will keep repeating it forever. So intrinsically, the random access is not going to work unless the load on the network is very low. Okay? It's not so bad in terms of fairness. Random access protocols are almost fairly fair. I mean, fair means I'm treating everybody in the same way. Statistically, you are treating every node in the same way. Yes, that's true. You need a long time scale to be fair, not on the short time scale. But on a fairly long time scale, you are fair. The access delay are very good if the network load is low. So we must run a network with a low load, average low load, and that implies that also the access delay are good. These are the most important parameters, not the only one. Robustness, ability to scale in terms of users, of size. There are other parameters, other issues. The three most important ones are throughput, fairness, and access delay. Now, in terms of throughput, the protocol I showed you before, the one with slots and reservation, is the best one. It's avoiding any conflict, so you can ensure 100% of throughput, fully link utilization, because you check and you only write if the slot is available. It's fairly good in terms of fairness. It's not perfect, because some node has a little bit larger delay, and it's fairly good also in terms of access delay. So from that perspective, it's a very good protocol. Still, it's not used for other reasons, but remember, in order to discuss performance, you have to look at throughput as a first parameter, and then at access delay. fairness is something that we must guarantee. There are tons of protocols which perform better than the one we are using simply because they are not fair. The empty slot is a typical example. The empty slot is a trivial protocol with no reservation. It guarantees 100% of throughput. It's completely unfair, so it's simply not acceptable. So fairness is something we need to have in order to make this protocol potentially usable or not. It's a kind of necessary condition. Okay? So, let me stop it here. You have any question? I mean, we have a few minutes, but if I start now, then we will stop the review part in the middle of a line of talk. So, basically, we will revise very quickly the random access approach, which is the most widely used today. Actually, I would say the only one which is used through the Ethernet standard without looking at too many details. And the basic idea is that we do nothing unless something bad happens. We already know that that's not the best choice in terms of throughput, amount of or ability to exploit the channel capability, but we are using it because we have in mind something very clear, which has an impact in terms of quality and resource utilization, that those networks that run with an average load which is low. That's why they are working and that's why they are popular. These networks, and actually we see most of the networks we are using today, are actually run in a condition in which the load is low. And under that case, everything becomes very, very simple. Even such a simple protocol may work in a good way. But if you try to increase the load on this network, which means that what the user tries to send globally is close to the link capability, those protocols are not going to work in a proper way. We know that. Okay? So we must avoid that as a good network manager. Okay, that's the end of the class, unless there are questions, but I think that there are not. So we will meet again together next Thursday.